Our agenda covers the chronological evolution of data centers. Starting with origins in World War II-era computing, we'll move through mainframes, the rise of on-premises servers, the internet explosion, cloud adoption, energy concerns, AI demands, and emerging trends like edge computing. By the end, you'll understand how data centers became the backbone of the digital world. Data centers trace back to the 1940s with ENIAC, the world's first general-purpose electronic computer, completed in 1945 at the University of Pennsylvania. This 30-ton machine occupied an entire room, used vacuum tubes, and needed extensive cooling and power. Primarily for defense projects, it marked the need for specialized facilities to house computing equipment, laying the foundation for modern data centers. In the 1950s and 1960s, the data center concept emerged with machines like the IBM 704. These required dedicated rooms with specialized cooling, power, and raised floors for cabling. Limited to large organizations due to high costs, every byte was valuable. These facilities transformed computing from experimental to operational, shifting IT from a novelty to a strategic asset. The 1960s saw transistors revolutionize computing, making machines smaller and more reliable. IBM's System 360 in 1964 introduced compatible family of computers, boosting commercial use. Data centers grew in offices and dedicated buildings. Early time-sharing allowed multiple users, foreshadowing cloud ideas. Security and redundancy became priorities as data grew critical for business. The 1980s brought microcomputers and client-server models, reducing reliance on mainframes. Affordable PCs and Unix workstations allowed distributed computing. Local area networks connected devices, leading to small server rooms in companies. This democratization made IT accessible to smaller businesses, but introduced challenges in management, security, and scalability. The 1990s internet explosion led businesses to build on-premises server rooms, often converted closets with racks of servers for web hosting, databases, and email. Security was basic, scaling expensive. These inadequate setups highlighted needs for better reliability, paving the way for professional data centers. Co-location facilities emerged, allowing shared infrastructure. Early 2000s saw purpose-built data centers with redundant power, sophisticated cooling, fire suppression, and security, located near fiber optics and grids for reliability. Businesses outsourced to these facilities for uptime and scalability. This era shifted IT from cost center to strategic tool, supporting globalization and e-commerce growth. Cloud computing revolutionized data centers in the mid-2000s. Amazon's EC2 in 2006 offered rentable virtual servers. Virtualization allowed multiple workloads on one machine. Providers like AWS, Azure, Google Cloud built hyperscale centers. Businesses accessed scalable resources without owning hardware, democratizing technology for startups and enabling big data analytics. The 2010s featured hyperscale data centers, vast facilities with thousands of servers. Tech giants invested billions. Edge computing brought mini-centers closer to users for faster response. Internet of Things, streaming. Hybrid models combined on-premises and cloud. This era supported mobile apps, streaming, and global connectivity. As data centers grew, energy use soared, reaching 1 to 2% of global electricity. Early PUE over 2.0, modern aim for 1.1 to 1.2. High-density servers increased power demands, straining grids in areas like Northern Virginia. This sparked focus on optimization and renewables to mitigate environmental impact. Sustainability became critical. Providers shifted to renewables, solar wind power. Innovations like liquid cooling, aisle containment, and AI-driven management improved efficiency. PUE dropped significantly. Companies committed to carbon-neutral goals, using metrics like PUE to track progress. Sustainable practices ensure long-term growth amid rising demands. The 2020s marked the AI era, with explosive demand for training models straining facilities. GPUs and accelerators require immense power and advanced cooling, like direct-to-chip liquid. Data centers redesigned for high-density AI racks. This drives innovation but challenges grids, accelerating need for efficient, resilient infrastructure. Edge computing decentralizes processing for real-time applications like autonomous vehicles and 5G. Small edge facilities near users reduce latency. This complements cloud, creating hybrid ecosystems. Modular designs allow rapid deployment, supporting IoT explosion and low latency demands in smart cities and industry. Technologies evolve dramatically, from vacuum tubes to GPUs, basic air conditioning to advanced liquid systems, centralized mainframes to distributed cloud edge. Virtualization maximizes resources, containers like Docker-enabled portability. These advancements increased efficiency, scalability, and supported complex workloads like AI, transforming data centers into dynamic, software-defined environments. Future data centers will emphasize flexibility with modular designs, possibly small nuclear reactors for power. AI will optimize energy and operations. Industry pushes for net zero carbon via renewables. Edge growth, quantum integration, and resilient hybrid models will support emerging tech-like metaverses and advanced AI, ensuring sustainable expansion. Thank you for watching, and see you next time.